And again, I'd like to thank you for joining us today. And with that, I will go ahead and hand it over to Jafar Shamin, who's a Business Development Manager here at Amazon Web Services. Jafar, you have the floor.
Thanks, Aurora. And thank you for joining this webinar. We'll be talking about PostgreSQL and how you can run and maximize the performance of your databases on AWS. With me, we have Miles Ward, Senior Manager of Solution Architecture at Amazon Web Services, and Jay Edwards, who is the CTO at Palomino DB. So the agenda today, I'm going to cover briefly what Elastic Block Store is and what Elastic Block Store Provisioned IOPS volumes are. And Miles and Jay are going to talk about Postgres, the best practices of running Postgres on AWS, and some lessons learned from the Obama for America campaign. So as you start using AWS, you have two broad choices in terms of storage that is available to you. Obviously, for Postgres, you will be choosing the block storage platform that's available on AWS, which is the Elastic Block Store platform. You can also use EBS to create file systems, run other databases, and enterprise and productivity applications such as ERP, CRM, Exchange, etc. The other option is Object Store, for example, S3 or Glacier. EBS has a facility available for you to back up your data in the form of snapshots. These snapshots go into S3. S3 gives you 11 nines of durability, so your data is safe. So a little bit about Elastic Block Store. So Elastic Block Store is a service that gives you high-performance block storage devices. So these are presented to you as raw, unformatted storage devices. And it's a service, which means we manage the heavy lifting to give you a reliable storage platform and provide you the storage when you need it to match the performance your application demands. So it's an on-demand block storage platform for you to use. You can provision volumes from 1 gigabyte in size up to 1 terabyte in size. And when you create an EBS volume in an availability zone, it is automatically replicated within that zone to prevent data loss due to failure of any single hardware component. You can create snapshots that are stored in S3, like I mentioned before, to restore point-in-time copies of your data. And EBS also provides you detailed metrics around performance and other characteristics of EBS through our CloudWatch service so that you can monitor your storage. So with EBS, you get two types of volumes, standard volumes and provisioned IOPS volumes. When you are choosing which volume to use for your application, here's some guidelines. So standard volumes are optimized for low to moderate IOPS needs and occasional bursts. They're good for boot volumes, running websites, log processing, file serving. When you want consistent performance for transactional workloads requiring consistent IOPS, you may want to choose provisioned IOPS. With provisioned IOPS, you can provision up to 1 terabyte in volumes and up to 4,000 IOPS per volumes. The slide says 2,000, but we recently announced that with each volume you can get up to 4,000 IOPS. And you can obviously stripe these volumes to get even more IOPS per instance, as Miles and Jay will discuss further on in the presentation. And provisioned IOPS are great for business applications running NoSQL and relational databases such as Postgres. So a little bit more about provisioned IOPS volumes. We introduced provisioned IOPS volumes in August of last year. And what they provide you with is consistent performance per volume, like I mentioned before. When you are choosing to use provisioned IOPS volumes, all you have to do is specify IOPS that you want, up to 4,000 IOPS per volume, and the capacity that you want. And you can do that easily using the web console or command lines using APIs that are available to you. So what are customers running on EBS today? We have seen great adoption of provisioned IOPS volumes, and provisioned IOPS volumes are being used by enterprises to run the Oracle, SAP, Microsoft workloads. There are a lot of gaming, social, mobile, and education institutions who are running high-performance transactional workloads, including NoSQL and relational databases. We are seeing a lot of marketing and analytics companies leverage the consistent performance that the provisioned IOPS volumes provide to run their analytics workloads. And we are curious to hear what else you may be running, feel free to reach out to me with any comments around Provisioned IOPS and share your experience with the EBS. My email will be at the end of the presentation. And there'll also be links to more detail about EBS at the end of the presentation that you can use to find out how to use EBS to get the maximum performance for your applications. Now I'd like to hand it over to Miles to go over Postgres and the best practices for using Postgres on AWS.
Jafar, thanks a bunch. I really appreciate the introduction. Elastic Block Storage and Postgres SQL on EC2 are kind of a match made in heaven. I'm excited to go through some of the research that we've done together with consultants from Palomino DB to identify and enumerate the best practices for Postgres SQL hosting on EC2. We have a lot of detail to cover today, so I'm going to try and move through it pretty quickly. This is kind of an early preview to a white paper that we're just about to release on the subject. So everybody can stay tuned for even more detail available in that view, but I think today's webinar will do a great job of providing a lot of very actionable insight into the right designs to leverage for PostgreSQL on AWS. So we hear from lots of customers that, sort of back to this other sort of component, that as an open source relational database management system that's feature rich, Postgres is a great choice and a workflow on AWS that we're seeing grow over time, in particular around GIS workloads and other sort of high feature relational functions. So a couple of basic concepts to master before you start to design a Postgres system on AWS. The way that replication works in a Postgres database cluster or fleet is you establish and define a master PostgreSQL host. That master node accepts both reads and writes and allows several different flavors of replication that allows high availability and read scalability and performance scalability for the database system. That's operating at the structural level. There's also, of course, the logical level of subdivision by way of database sharding. So masters are called masters in PostgreSQL, and secondaries are called secondaries, where you're able to receive write-ahead logs from the master and then either perform synchronous or asynchronous replication using those logs. You can also either have sort of asynchronous with the attempt to be as on time as possible, or an intentional delay to create sort of after lower performance impact copies for reporting or other kinds of analysis. So to get started with Postgres on EC2, really, this is a pretty well used and well liked piece of software. It's available in many, many different repositories. So you can really start with the Amazon machine image of your choice. AWS has its own Linux image called Amazon Linux, which is one that we maintain and support. If you're a customer of AWS premium support, you'll find that they have the ability to support you full stack if you're using that operating system, as well as a couple of the other sort of named operating systems, like they can help you make connections into folks from Ubuntu and Red Hat and the other teams. Once you have a machine image that you like, you'd launch an EC2 instance and attach EBS, an EBS volume or EBS volumes to it. Those volumes are where you'd store the data for the database. We have lots of customers that make the mistake of storing the database on the root volume of the EC2 instance. The root volume is not designed for that kind of storage, and is more complicated to resize if that's what you need to do. So following that installation and assignment of drive resources, you'd install software from the PostgreSQL either FTP site or their repository. And then in order to allow database connectivity to your EC2 instance, you'd open port 5432 to allow inbound traffic or ingress traffic. In VPC, you'd have to make sure that you allow that not only at the EC2 security group, but also at the network ACL or the subnet security group to ensure that the traffic that you need to get to the instance can get there. In a master-slave configuration where you do have a secondary node, which is the recommended design for all production deployments, you also have to alter the master-slave configuration file inside of Postgres to enable write-ahead logging senders to increase the maximum from 0.
This is Jay.
Yep.
That Maxwell Center's value requires a database restart to change. So it's best to set it a little higher than you think you might need. If you think, I'll have a master, I'll have a few replicas, maybe you want to set it to about 4. So just something to bear in mind.
Yep, absolutely right. So we also recognize that AWS has some very high performance instances. We've chased after some of the larger infrastructure fleets in the world, and we've designed 2 systems now, the High1 4x large and CR1 8x large, that have solid-state disk storage for local ephemeral disk. And if you're going to use that SSD storage, you want to make sure that those are unlogged tables. Otherwise, you're going to consume a lot of the available performance that's there with SSDs. And you'll also want to make sure that the file system used is configured correctly, that the alignment to block size inside of the SSDs is done correctly. You have to make sure that you've got any of the real data that you're using stored somewhere in durable storage and persistent storage. SSD storage on either of those 2 instances is ephemeral. So if the virtual machine stops or is restarted or not rebooted, but if it's stopped and started or terminated, or if there's a problem with it and it fails, you'll lose all data in that SSD storage. So it's one of the important drivers for implementing on top of EBS. So to kind of make that a little more visual, if you look at kind of a basic design, we see this getting done over and over and over again. AWS is built to deliver high availability by way of the multi-AZ design pattern. So we have multiple sets of availability zones inside of regions that allow you to have the fault isolation and independence of separate data centers with the tight interconnectivity and high performance networking of typically inside the building. So the design to distribute the master and the secondary from across 2 different AZs really amplifies the fault tolerance benefits of the replication that Postgres enables. So a couple of replication basics. You are, again, the records that you write to the master are transferred to the secondary using a function called write-ahead logging, or WAL. That replication can, again, be real-time through a mode called streaming replication, or it can be a delayed copy, so an archival or reporting-oriented copy that's done at a lower performance impact to the master. Those 2 different timing models are independent of the settings around durability model, whether you enforce synchronous replication where the remote secondary has to acknowledge the completion of the write locally before the master can acknowledge completion, or asynchronous replication where the secondary just has to move it to try and keep up. You can can keep multiple additional secondaries online in order to provide additional candidates, additional instances to fail over to if there's a problem with your existing secondary. That's you can also do that in that sort of a cascading mode with cascading replication.
This is Jay. I have a few comments on that last slide.
Yeah.
So something to pay attention to with synchronous replication is that it is very network sensitive, right? So if you have a lot of network latency or you have a lot of problems, it can kind of slow down the entire process of your master, your database. And the write-ahead log is actually how, even if you're not replicating at all, Postgres has a wall. It's the method that it uses for asset durability, right? So like on MySQL, you've got an InnoDB log file. It's just, this is how, it's basically, it works kind of the same way Oracle does, right? You're basically streaming the transaction log, and that's how replication happens. Back to you, Miles.
Sure. So an important, add-on to that, one of the things that I think folks miss in the EC2 instance specification definitions is the I/O capacity or I/O capability listing associated with each instance type. Different instances have and come with a consistent amount of network bandwidth that's available to them. We'll talk about EBS optimized as a flag you can set to improve the bandwidth between your instance and EBS to provide a guaranteed amount of bandwidth to storage. But independent of that, larger instances have a larger amount of network bandwidth. So you may find that you have plenty of free memory for your workload and plenty of free CPU, and you're unloaded in those ways, but for replication purposes, you need more network bandwidth. You may have to evaluate different instance types to provide you enough bandwidth to stay replicated. So next kind of area we want to go through is some production design. How would you implement storage and instance configurations for EC2? We found with customers that barring the use of sort of third-party sharding or data replication or data distribution technologies, that you are driven in many cases to increase the number and the sort of resources associated with the master node and to scale up slave nodes in tandem to deliver the amount of write and read capacity that the whole database system requires. The replication technologies that are available increase availability and allow read scalability, but don't offer the kind of, a multi-master write scalability that some other infrastructure database types do. So you do end up driven to a design where you will end up vertically scaling that master node, and typically it's best practice to have the secondary nodes be the same size as the master. Provides all sorts of benefits in terms of them having the same amount of network bandwidth and them having comparable memory footprints. That vertical scaling today on AWS is possible all the way up to that CR1 8x large size. So that's 16 cores hyper-threaded and 244 gigs of memory on 10 gigabit full bisection, zero over subscription, non-blocking network. So that represents a pretty massive database machine. We are certainly seeing customers deploy Postgres at that scale, but they do so far with pretty significant headroom. We also recommend, as you're looking through different instances, and we'll show some mechanisms for this, tuning the Postgres engine to accommodate the actual CPU and memory resources that each EC2 instance makes available, and absolutely looking at either third-party technologies or your own logical subdivision across database engines to create the kinds of write scalability that you might need. Replication does a lot to support read scalability, in particular for heterogeneous read loads, like the difference between your production application and your reporting systems. So things not to do, things to sort of double check against. One, we certainly see customers that put everything in the kitchen sink and every picture they've ever taken and all kinds of data that probably doesn't have a particularly important reason to be stored inside of what's effectively the most expensive kind of storage system, a relational database. And so we certainly recommend, as you're looking through your application design, like Places where it puts pictures in the database, that's a real low-hanging fruit. You've got to figure out a way to pull the pictures out of there. You may not need to do everything that you're doing with a database in a database, and that can have a really significant cost impact around the usage of something like that. We also want folks to recognize as you look at vertical scaling in comparison with horizontal scaling, there are structural benefits to a horizontally scaled mode where by being distributed across additional instances, you move from sort of single points of failure to having the opportunity for redundant multi-point systems. And so it's important to capture also the ability that delivers to scale in smaller units. So if you're able to shard and distribute it across multiple database masters, you can build those out of relatively smaller instances, and as a result grow by small instance values rather than adding the next bigger instance size, which is usually twice as expensive. So another part of this is we definitely have customers that are eager to follow what they think of as the kind of Amazon way, where they kind of auto scale to the size that they think they're going to need, and they haven't done a lot of research around the sort of scale that they expect to deliver on top of AWS. That's okay, and certainly we're a great place to experiment and learn. But if you know for a fact that you're going to need a big system, there's no real reason to sort of scale up step by step. You should build a system that's designed to accommodate the performance and the workload that you have, and deliver that to you at full size right at the get-go. There are operational costs to sort of slowly stepping up and maxing out the database and then resizing it to the next size up. So from a minimum scale, we really recommend, and this is something that we can say pretty clearly across all conceivable use cases, EBS adds very tangible value, very significant performance advantages over standard ephemeral disk. Always use elastic block storage of one type or another in the presence of your databases. Standard EBS provides really significant write cache, and so especially for very small databases, is kind of bigger than its britches, capable of swinging for the fences every once in a while. Now the flip side of that is that for production, macro scale databases, provisioned IOPS offers much more consistent I/O delivery, and as a result, it's something that you can, provide random I/O performance at scale. That's something that you can, measure against and rely on and make sure is, very, very consistent over time. So as you scale upwards, from say, even medium or small instances running Postgres, as you start to move on to, our larger instance classes, we see the majority of production databases today are running somewhere in the extra large class, an M1X large. Maybe they're stretching on an M1 large, but certainly, M24XLs, M22XLs, very popular database machines. As you move into those types, you're able to use EBS optimized as a flag, which provides dedicated bandwidth to the EBS subsystem and supports the consistency design of provisioned IOPS. So we really strongly recommend as you move up to this scale, if you're into M1 larges or M1XLs or M22XLs or 4XLs, it makes a lot of sense to move on to provisioned IOPS as well, because you likely will be bound by disk performance relatively early at those scales. So with for example, an M1 extra large, assuming the default value from Postgres as 8K block operations against disk, and given that you can deliver EBS volumes at up to 4,000 IOPS, you can attach 4 volumes in RAID 0 to an EC2 instance and be right at the sort of maximum throughput, almost a gigabit a second to and from storage. That works out to 16,000 IOPS at 8K and delivers, frankly, a very, very high performance database from a structured storage standpoint, one that would be easily 16 times as fast as was possible on AWS just 2.5 years ago. So that kind of design, moving to multiple EBS volumes, does mean that you need to use either MD-ADM or LDM RAID. We have some folks that implement logical volumes above MD-ADM. That works fine as well. There aren't very significant performance impacts there. And it's important that you use correct settings around block size alignment, for your application inside of MD-ADM to ensure that the file system and the RAID controller all line up with the provisioned IOPS storage. Anything to add there, Jay?
Not really. One of the things I do want to step back to, when Miles was talking about the fact that databases have an associated cost, right? They really are the most expensive form of storage for your data. That's not just at a hardware level, right? Databases require specialized operational expertise that's a little harder to find than some other things. So I love databases, right? It's what I do professionally, but think carefully before you start shoving everything in the database because it's easy.
Yep, good call. So we definitely have customers that for whom the sort of M1X large size or the M2 4XL size does not cut it. They need higher performance than that and greater throughput. And there's some confusion as to how much additional performance the larger cluster compute instance types provide. First off is they are connected by an absolutely amazing network system, and that network system allows them very, very, very rapid and very low latency communication instance to instance. So in particular, if there is network lag that's driving replication delay, the cluster compute instance types are easily an order of magnitude lower latency between nodes, particularly in placement groups where you're talking about targeting at the 70 microseconds latency rather than measurements in the millisecond range. So in addition to that, they do have higher throughput to storage. So you can roughly double the design that you would implement on an M2 4XL or an M1 extra large on CC2 by going to 8 provisioned IOPS, 4,000 IOPS volumes. That gets you to 32,000 IOPS to storage, which is really competitive, if not, from a consistency and durability standpoint, faster than the current SSD hosts in the High-1 4XL. It's certainly faster than the storage, the somewhat smaller SSD storage on the CR1 8X large instances. So this represents the fastest write mode for Postgres available on EC2. Now, where it doesn't beat the SSD hosts is on the read side. Read scalability from those hosts is incredible. They're able to deliver in excess of 100,000 random I/O reads a second. And so you may end up in patterns where you're combining those two services. So certainly also want to make sure as a RAID configuration tip that you're setting the effective I/O concurrency equal to the number of stripes in your RAID set, in this case 8. So little typo on the next screen here, but as a model, there's no reason that you can't combine somewhat heterogeneous fleets here. The CC2 8X large has the same amount of memory as the High-1 4X large. Both have 60 gigs of memory. And so the High-1 4X large can be really spectacular read secondaries attached to a CC2 8XL master. This pattern delivers the highest read throughput of a multi-node system on EC2 today. There isn't any kind of specific advantage to going to the CR1 8XL unless your entire data set or the vast majority of data set could fit in memory at the 244 gig size, at which point you're not bounded by storage at all and you can just tear away at reads. But at larger data set size, up into the 2 terabyte range, that's where the High-1 4XLs will be the most efficient of the choices. You also want to make sure that there are certain integrity features like fsync and full page writes on SSD hosts that are kind of irrelevant because they're ephemeral hosts anyway. If you have a problem with one of those instances, you just get rid of it and create a new replica.
This is Jay.
Yeah.
I want to reiterate what Miles is saying. This combination of hosts really is kind of the top-end performance you can get out of AWS. I also want to tie something in from an earlier slide. There was a little bit of mention with temporary tables and SSD storage and creating your tables as an unlogged type. What that unlogged means is that writes to that table don't go to the wall. Now, the downside to this is that if your database crashes, the tables get truncated. But since we're talking about disposable SSD instances, that's another thing you can do is to alter those tables to be unlogged. It's a little bit of work, but it drastically improves performance. So in combination with turning off the fsync and the full page writes, you can eke out just the absolute fastest reads and writes off of those SSD replicas.
Awesome. So don't take us at our word. We are saying it's fast, but, we're just a couple of nerds here. It may make sense that you do your own tests. We don't have, any problem with you spinning these machines up and kicking them hard and making sure that they deliver the performance that you'd expect. You can certainly do sort of direct sequential test examples, but typically we're seeing, sort of sysbench or FIO or, other kinds of test disk systems or disk-oriented test systems, IOZone and others, as reasonable approaches. We have a couple of different models for that. We also are seeing a lot of customers wanting to do this native inside of the database engine. So you can use pgbench to build a Postgres database for testing. You can do multi-client tests, high transaction count tests, all of the kinds of benchmarking that you would normally do on a physical server. There's no reason you can't do that on AWS. And the nice bit is that if you don't like the computer that you just benchmarked, you can turn it off and pick a different one or configure it differently or run a bash of tests against 20 different machines configured differently to figure out which one is optimal given the settings that best reflect your workload. So you also want to make sure that as you follow these designs, there are lots of different implementations against the database configuration systems. You want to make sure that it's configured in the way that you intend to use it. Like, for example, if you are going to use pgpool, you want to test against that instead of testing against DB. We also want to make sure that as people are designing these systems that they're planning not only for high availability by way of distribution across multiple nodes, but also for disaster recovery. We hope that nothing ever happens, but it's very important for business continuity to have a reasonable backup. So EC2 provides this very powerful capacity that's a part of the EBS design called an EBS snapshot, where we duplicate content to S3. That duplication happens as a background process. Once it's started, it just sort of tears off and copies that data into S3. There is a performance impact associated with performing snapshots. And so it's important to try a snapshot on a given database to view what that looks like given your actual workload and how heavily you're loading the storage performance on a given disk subsystem. Do not underestimate that is a real impact and that it's something that you should test and measure. It's definitely there. And as a result of that, it may make sense if you are right up near the maximum capacity for your systems that you use a replica, create a new streaming replication, or a delayed replica of the database, and then snapshot from that, so that you don't have an impact on the production master.
This is Jay.
Yeah.
I would, personally speaking, from my experience, I would always take a snapshot from a replica. I mean, if you've got a production box that isn't doing production stuff, sure, but most of the time people do care about performance. So in general, just to be safe, because I'm kind of a conservative database guy, I always like to take my snapshots from replicas.
Yeah. I get that for sure. I guess I'm thinking there are definitely customers that are down at the, my Postgres system is an M1 medium with a single EBS volume attached, and you don't have any replication set up. That what I want to make sure is that it is entirely possible to take a snapshot of your production system. But Jay's absolutely right. In any kind of scaled multi-node, full-size web-facing production system, it's very, very, very much the best practice to snap from a replica. So, and then to restore, not very much fun to make a backup if you can't get it back. You can use our API or CLI command to evaluate which snapshots are where. Operationally, in practice, it can get really complicated to tell which one's which if you're not really consistent with naming and tagging. So strongly recommend that you kind of keep your own index of, we made a snapshot at this time of these databases and those IDs were these IDs. That way you're able to recreate from snapshot that database system quickly. You can also, if you want to be more comprehensive about it, if you are using a replica, if you can detach, the replica from the rest of the system, kind of turn off replication, then you can even bundle that whole service as an AMI. So what that does is captures the operating system state and the root volume state, as well as the volumes that are attached into a single ID rather than these individual IDs for each snapshot. The downside of that is that you kind of have to start all of that at once. One of the advantages of an EBS snapshot is you'd be able to just start the EBS volume and attach that independently, maybe for forensics or some other kind of function. It's really important to have, in particular when you're talking about EBS volumes where they are connected by RAID, to create a consistent snapshot. If you start one snap at one time on one volume and then wait a little bit and then start the snap on another one, which is what you would do if you were doing it through the user interface by hand, it would be very difficult to get the two disks into a consistent state. So it's important that you're, either at the file system level, creating a file system free like you can do in XFS or ext4 or otherwise suspending rights to storage to ensure that you're able to take a snapshot where both sides are consistent. The folks from Aleistic, that's ALESTIC, those are engineers from Ubuntu. They have a set of scripts called EBS Consistent Snapshot that make it easy to take that kind of multi-disk snapshot when a RAID stands above them. Any other notes on that bit there, Jay?
Not really. I think you covered all the high points. The one thing is you can tell Postgres that you're taking a backup of it. We saw that a few slides ago. And that's important to do. Let it know. Let the database know you're going to take a backup. It's going to quiesce things. It's going to make the database internally consistent for you to take the backup.
Yeah, that's a good recommendation. Make the database consistent, and then make the disks consistent. Let me go even further. Make the database consistent, then make the file system consistent, then make the disks consistent, and then stick them in storage that's indestructible. So that's a great sort of stair step to walk yourself through. Another spot is there's definitely places where you can adjust, both the settings for the kernel and and the sort of basic memory management settings of your instance, as well as the file system, to ensure that they're set in a way that delivers the maximum performance. I mean, in particular, the making sure that SHM max and SHMall have very, very, very small values to start out. So you probably want to raise those values. You also need to make sure that VM swappiness is is set low so that you don't have just sort of this incredible amount of swapping to disk. One of the other practices there is you may want to use on instances that have local ephemeral storage, like we were talking earlier about M24XLs or M1X larges, put the swap for the operating system somewhere else than that root volume. Put it on the ephemeral disk. There's no cost to using that storage. It's ephemeral. It may die. It could fail at some point, but the performance benefit of moving that kind of swap activity off of, particularly definitely off of the provisioned IOPS volumes that you're using for your database, where now your swap is contending with disk performance for database, that's a real bad thing. Also want to make sure that your file system is tuned well. No barrier, no atime, no duratim, no exec. Turn off a bunch of these functions that don't add value to the database system, because that's what you're using the disk for, and that makes things run a little quicker. Another whole area is kind of wall optimization, wall tuning. Jay, is this one you want to go through?
Yeah, in fact, I was actually going to start talking about some of this stuff, but you got this slide. Okay, so the wall is the write-ahead log. It is basically the database's journal file. We strongly recommend XFS. If you absolutely had to, for some reason, I suppose you could use ext3. Do not use ext4. It's the same reason we don't recommend that people run MySQL on ext4. When you're doing direct, there are some thread contention issues that can cause fsyncs to kind of hang out for a while on ext4. There is very recently a new mounting option. Unfortunately, we haven't tested that yet, so I still can't say use ext4. In general, we have a lot of clients, we run a lot of databases, XFS everywhere for databases. So the checkpoint segments, the number of checkpoint segments, and this is analogous to kind of tuning your InnoDB log file size. It's how often are you going to want to checkpoint your data and write it and kind of flush it out of the wall. And this depends on how quickly you modify data on your database. So it's one of these things that you start off small and you kind of monitor your log file. You can actually grep for hints, and it will say, hey, your checkpoint segment's too many, you got to make it a bigger number. That last point about ext3 we can skip, and it's the same thing with the file segments. A lot of the tuning on Postgres depends on how quickly you modify your data. So you need to have a good idea. You need to monitor your logs and just kind of look for it. It can drastically affect the performance of your writes. And memory tuning. So this is actually one of the biggest problems. Shared buffers, just for, I feel like saying almost everything. And it's really difficult to kind of plan out beforehand. It's like, how many connections am I going to have? What's the maximum number of connections I'm going to have? And just kind of a quick rule of thumb is to start off with 25% of your RAM, or 25% of the RAM that you're going to allocate to the database. There is a script. It's called pgtune, and it's pretty good at making a base set of recommendations based on the hardware that you have available. It's definitely better than just kind of throwing the default Postgres on there and running with it. The default Postgres installation is just about only good for running on a developer laptop, and not even then very much. Miles, back to you.
Sure. So, it's one thing to have a database and have it go mega fast. It's another thing to not have a clear view into consistency of that performance. And there's a lot of metrics that are, critical to evaluating on a regular basis to ensure that the database is performing the way that you want. We've seen, a lot of value from customers using, using custom metrics. So standard EC2 is connected to a service called CloudWatch. CloudWatch allows you to monitor some basic functions from instances like CPU utilization and disk utilization and network in and out. But we've published, the link below is a set of scripts that make it easy to publish net new metrics into CloudWatch as custom metrics. And that publishing function means that those show up in the same dashboards as the CPU and network and disk utilization measures. It's stored and queryable from there, so you can kind of have a centralized place to deliver all that stuff that you don't have to manage from a storage standpoint. And these 5, keeping track of connections, keeping track of memory usage, I'd certainly add to this list probably free disk space as something that we're not measuring, because that would mean, sort of bad things. So it's important that you're able to take a look at the measures that affect your database. There are certainly additional, open source as well as commercial options for charting and graphing and monitoring and performance analysis inside your database. But this is one that you can take a look at right next to your existing AWS monitoring services. So last kind of area that we're seeing, we want to make sure that everybody understands there are really significant security options, really important steps that you can take to ensure that the database is well defended from all the sort of different potential attack vectors. Really recommend, encryption is available at several different layers: the connection layer, the row layer, and at the full file system layer. PG crypto is pretty well understood and does a good job of creating that kind of in-database encryption. We also provide very robust systems at AWS around authentication and network, to ensure that either you're connecting to that database internally between security groups where the routing table is, very explicit, and the database is stored and hosted inside of a private subnet. We also recommend, for management connections and other things, using VPN or other encrypted communications to and from the server. And if I could put it in a bigger font and have it fit on the slide, I would. Please, everybody, use identity and access management to construct rights-limited credentials for yourself, for your developers, and for your applications to ensure that they access AWS APIs with the minimum of rights. So if your users, have super tight controls inside of the database to ensure that they can't do anything they aren't authorized to, but they have an unlimited rights user inside of identity and access management, or using even worse, the root credentials for your EC2 instance, then just turn the database off. So really important to provide control at all of the different tiers of your stack. And IAM also supports multi-factor authentication, so you can require your administrator to use either an authenticator from your phone or a physical authenticator token to ensure that at least access to the AWS APIs is highly secure. So, Jay, I think you had a couple of extra notes specific from the stuff we did together at the Obama for America campaign.
Indeed, I did. So at OFA, we were extensive users of AWS. I believe we used every single service that they provide. And at some point, we had reserved very, very large amounts of some of the U.S. East infrastructure. So I'm going to talk not really about technical stuff, but some of the lessons learned, right, over this year's time, 18 months' time. The first thing is AWS puts out a lot of documentation. It is sometimes difficult to get through. There's a lot of it. It doesn't seem to be fantastic to search. Almost every problem I have ever had shows up in the documentation, though. So it is well worth spending some time to really read through and understand the documentation for the EC2 and EBS, and any new service that you're going to use. Spend a little time. There's a ton of information there. Number 2, always use provisioned IOPS. And it's not so much about the performance, it is about the failure rate. I am not privy to any magic numbers, but my anecdotal evidence suggests it's maybe an order of a magnitude better failure rate. So any production system where you care about the disk drive, even if you don't need all the PIOPS, just pony it up for the smallest 100 IOPS version. Now, obviously, for web servers, this doesn't matter. Who cares what they have on their hard drive anyway? Enterprise support or business class if you're not quite big enough, absolutely worth it. Absolutely worth it. I believe the entry fee for the top level enterprise support is $15,000 a year, a month. What, Miles?
Yeah, it's $15,000 a month.
If your business relies on AWS, it's absolutely worth it. 100%, no question. And it's hard to look at that and be, that's a lot for support. It's amazing. Something that nobody ever talks about that, for me, I always get very excited about is how easy AWS makes inventory management. There are a number of times in my career where I have had to rewrite this system that is like, keeps track of what systems I have deployed and what systems are up and what systems are down. And it's always very difficult when you're running a large network to keep that inventory tracking system up to date. It normally turns up, you end up having a team of 1 or 2 people that basically their whole job is to kind of keep track of servers. With AWS, it's the console is always up to date. The command line is always up to date. You can always run a command and understand, oh, these are all the servers I have running. These are all the servers that are off right now. I will tell you, though, it's easy to have a server running and not know about it, right? You're like, oh, AWS, we just fire up another server. So it does make a lot of sense to kind of take that inventory and cross-check it against what you think you should have running. But the actual mechanics of getting the list, the accurate list of what's running is really, really valuable. If you're paying for AWS Business or Enterprise support, you have access to the Trusted Advisor. Now, let's say a year ago, maybe a little longer than a year ago, the beginning of last year, it wasn't very good. It didn't tell you a lot of stuff. It would be like, you have some servers, and they're not doing a lot of CPU that we can see. It is much, much, much better now. It makes a lot of very smart recommendations. It can help you avoid that problem I just talked about where you have servers up that aren't doing anything and you don't know about them. So I'm not going to say it's worth paying for enterprise support just to get access to the Trusted Advisor, but if you do have a support contract with AWS, it's valuable. It's a great tool. You should look at it. I think the last time I logged in, there was a link just on the right-hand side of the console, so it's very easy to find. This is this next point about the product lifecycle. It really just kind of a meta point. AWS releases a lot of products, and in the beginning, I hate to say this, some of them are not very good. Or maybe they only meet like 60% of your use case. So you start something up and you're like, this is pretty good. It covers a lot of the common things that I want to do, but it doesn't do this or it doesn't do that. Oh, RDS multi-region replication. Oh, very fast snapshotting, which has gotten with EBS, which has gotten faster just recently. So I want to assure you that every single product I have used, which is all of them, they all improve at a dramatic rate. They get much, much, much better. So even if a product doesn't fit your needs right now, you need to keep an eye on it, because in 6 months or 8 months or 12 months, they're going to add features. The people working at Amazon are not idiots, and they know where they have gaps in their products. So even if something isn't a good fit for you now, keep an eye on it. And finally, and this is something that I've complained about and they need to work on, they have so many products and there are so many feature improvements, it's very hard to keep up to date with everything that's coming out and everything that is available. So that's actually one of the reasons why it's good to pay for support. If you do have that enterprise support and you do have a technical account manager, please be a little proactive for you. But I mean, it's a good problem to have, right? There's so much awesomeness, it's hard to keep up with it. And that is what I got for you.
Jay, I really appreciate the kind words. We'll try to keep up with the additional awesomeness. So we're at the spot in the webinar now where we can take a little bit of QA before we wrap up. Got a question here about some of the stuff that we said about CloudWatch. One part was asking, like, is CloudWatch a complementary service? So CloudWatch is free for the existing basic metrics at a 5-minute grain. We'll charge you a penny per instance per hour to add the detailed grain of 1-minute view, and there's a separate charge for custom metrics at a monthly rate. So there's charges to do the stuff that we described here, but there aren't charges for the sort of basic CPUs and things like that. There's another question that came in that asks pretty bluntly, are you saying that SSDs are less reliable than regular disks? So no, it's not what we're saying. Amazon has built instance types and services where an EC2 instance has a structure where if the disk is local to the instance, then it's ephemeral, which means that if you turn the instance off, the data on that disk is destroyed, or is unavailable to you. So it's certainly less, quote, reliable than the storage on an EBS volume, where if you turn off the EC2 instance, the data is not deleted and is present in a persistent state that can be moved from server to server. So that structural difference between the two provides the kind of patterns where you would end up using SSDs in kind of a replicated mode. It's not that the physical devices would fail more or less frequently. It's that the abstraction we've placed on top of them creates a kind of one is optimized for durability and the other is not. We have a couple of other questions that have come through. Are there official AWS AMIs, perhaps for each of the sizes that come with Postgres, pre-installed or pre-configured? No, we haven't done that yet. We've thought about it. There are a couple of different machine images out there that do have Postgres already installed, but we're looking our side on what it would take to curate up a list like that, and we'll keep communications with that kind of thing posted publicly. We are running right out of time. I'll make sure everybody can see this sort of last bit, where we really do encourage anybody that has questions about Postgres or about EBS to contact Jafar, and we have lots of places where you can get the slides and more information about benchmarking, including a really great article that was a coincident release with the 4,000 IOPS provisioned IOPS volumes from the Palomino DB folks. Thanks everybody for taking the time with us today. Really appreciate the good questions and hope to talk about more high-performance stuff again with you soon. Thanks, Jay, also for participating. Really appreciate your help.
Thank you.